Exercise 3. A box with an open top is to be constructed from a rectangular piece of cardboard with dimensions 5 inches by 28 inches. By cutting out equal squares of side X at each corner, and then folding up the sides as in the figure. Okay, that means we will end up with a box like that. Express the volume V of the box as a function of X. So let's try to find out the volume. I will erase this. Okay, first of all, the volume is simply length times width times height. That's our length. Should be a little bit straight. Let me try different pen. That's the length, okay? That's the width, and that's the height. And we can easily say that the height is simply X. Okay? That means height is X because we can see that's we were folding. Now, this is the width, and that distance, that line segment is the length. Okay. The quantity A, the length A is 28, the length B is 5. And in order to get that width, what we did from the distance 5, we did subtract X and another X, which means the width is simply 5 minus 2 times X. And respectively, the same, the length. From the quantity 28, we did subtract 1x and another x. 28 minus 2x. Okay? We do have all of the values. Now we just have to place them in the formula. The length is 28 minus 2x. The width is 5 minus 2x. And the height is just x. We have to distribute everything. I will factor out 2 from the first parenthesis, 14 minus x, 5 minus 2x. I can't factor out 2 because 2 is not a common factor. Okay, 2 and x, I can keep it, that 2 and that x. I will keep it in front, and then I will distribute this. 14 times this, 14 times this, x times this, x times this. Okay, 14 times 5. You have to help me, but I believe is 70. 14 times negative 2, negative 28x. Negative x times 5, negative 5x, negative x times negative 2x, positive 2x squared. Okay, I can keep working with green. And now I have to do the same for, or maybe I can simplify in the parentheses. 70, and then I have 28 and negative 28x and negative 5x, negative 33rd x plus 2x squared. Okay. And now we will distribute again. 2x times 70, 2x times 33rd x, and 2x times 2x cubed. The final answer is, I can possibly start from the last term because it has the highest degree. 2x times 2x squared, 4x cubed. 2x times 33rd x, negative 66x squared. And 2 times 7, of course 70, 140x. Excellent. This is the volume in terms of x. And I believe one of the options looks like my solution. Okay, that means what we were doing, we were creating a function, a model, the function that represents the volume of the box as a function of x. Let's check another exercise that we're supposed to solve in this week. Okay, let's try another one. A rectangle has parameter 24 meters. That's we have a rectangle, which is, let's say, A and B, and the parameter, which is 2 times A plus 2 times B. It's simply 24. And I can possibly connect them. I can say that 2A plus 2B is 24. Dividing each term by 2, I will get A plus B is 12. A little bit easier. Okay, that means I do have, based on that information, we do have some relation between A and B. A and B addition is just 12. Express the area of the rectangle as A of L, which function? Well, L is the length of its side. Oh, that means I'm supposed to change this for L. And it's okay. I can change for L, no problem. Or we can keep it. Okay, that means length plus B. B will be width, or if we like, we can put W. Oh, not. It's still good. Okay, length plus width is 12, but now we need a function A of L, okay, which is just the area, which will be length times width. But we like the function just in terms of L. L can stay, but I have to find a way to rewrite W, the width, in terms of L. And of course, that box will give me this information. I can solve this equation, the boxed equation for W, and I will have 12 minus L. 12 minus L. Okay, and let's distribute. L times 12, 12L. L times negative L squared. This is my function A of L, which is the area as a function of the length. And I don't know if I see that option. Yes, I do. 12L minus L squared. Okay, let's check. Okay, another scenario and another function. An open rectangular box with a volume 8 cubic meters has a square base. Express the surface area of the box as a function S of x of a length x of a side of the base. Okay, that means we have a rectangular box. Okay, I can draw a box. A little bit of 3D, oh, too long. Okay. Okay, let's say, with the square base. That's what I thought will be too many unknowns. That's the square base, and this is the height. Let's do a little bit. Oh, that looks like a cube. I didn't want, but okay, I can put x and x as a side of the base, and I will put h. Okay, h is a little bit longer or shorter than the base. Okay, okay, and we know this, that the volume, it's 8 cubic meters. Volume is also length times width times height. Length times width times height. X times x is x squared. And now, combining this and this, I can get an equation. X squared h is equal to 8. And possibly I can solve for h, 8 over x squared. Okay, yeah, that's just one thing. We have h in terms of x. That's what we will probably need. Okay, now the surface area. Okay, we do have a base, which is this. The area of this is just x squared. Plus, we do have 4 sides. This is one side, the back, another side, and the front. I will leave front open. But we have 4 of them, and they are the rectangles x by h, xh. Perfect. We almost done because we need that surface area in terms of x only. That means I'm okay with x squared, I'm okay with 4x, but h I have to rewrite in terms of x, which we do have it, 8 over x squared. Okay, this is x squared. 4 times 8 is 32, and x over x squared, just one x will stay. Okay, this is the final answer, and I believe it's this one. Excellent. Let's see what else we have in this section. Okay, the last part for this week was section 1.5, 1.1.3, and this is just still we're talking about a function, but we're talking about the new function that we can get from the old functions, which basically it's some algebraic operation we can apply on the given functions, and some compositions and some transformation. That means first thing we have to just recall some movement transformations. That means we should be confident with the vertical and horizontal shift, and we know that when we adding a number to the entire value, the function will go up. When we subtracting, the function will go down. That's when we're moving in the vertical. When we subtracting or adding just from the x, we actually moving in the horizontal direction. Okay. Now we have some vertical and horizontal stretching and reflecting. That's when we multiply by the factor c, and the factor c is like greater than 1, function will be just like a little bit higher, because each value will be bigger. This will give me a little bit smaller values. This will shrink like horizontally. This will be stretched horizontally, and that's also too important, the reflection about the x and the y-axis. Okay, and let's see the question. Suppose that the graph of f is given. Describe how the graph of the function f of x minus 3 and then minus 3 can be obtained from the graph f. As we know that this is then when we subtracting a number from the entire value, then we actually shifting down, 3 units down. So I would like to see not that, this one on this one. And then when we subtracting the value from x, this means that we actually moving to the right. Okay, it's like a little bit different, like that means we will shift the graph 3 units to the right, 3 units down. Okay, some absolute values. You can pause the video and read this, and I have the question. We of course know how to sketch the graph of the absolute value function. Do I have some? No. Okay, I can possibly start. So we know absolute value. Probably everybody is confident. That means this is simply absolute value. Or because we know the definition, we know the graph almost like from it's because we practice and we saw this so many times. But what I can also say, I can draw this like a general way or description, the algorithm of drawing absolute value of the entire formula. That means I can draw the function which is just inside. Oh, no. Where am I? Here. I can draw, because inside I have just x. X is just the straight line with the slope 1. Let me put the axis. Okay. And now, in order to apply, or in order to respect the absolute value, what I will do? Absolute value of positive numbers, everything what is above the x-axis will stay, because absolute value of the positive numbers are the same numbers. everything what is negative, absolute value of negative number, becomes positive. That means I will do the reflection. That we don't need this part. Yeah? Everything what was below has to be above. And that's the way to get graph. A little bit. Okay? Now, let's try to use the same idea and sketch that graph. That means, first of all, I will do x squared minus 1. My pen is, yeah, it's so weird. Okay, let's x squared minus 1. We know the parabola x squared, okay, and we will just shift it 1 unit down. Oh, something is not letting me to write nicely. Like that one. Oh, why I can't? I just wanted to. No, give me the nice. Okay, this is x, this is y. Oh, maybe I should wait a little bit. Okay, now again, x squared looks like that. Okay, and shifting everything 1 unit down looks like that. Of course, none of the lines should be dotted. I just want the nice solid curve. And now let's use the same idea. Everything what is above the x-axis will stay. That means this is the above part. Above means positive because that's the positive part above the x-axis. Absolute value of positive numbers is a positive number. I mean the same number. Now, everything what is below, which is that part, that's negative numbers. Absolute value of negative numbers are the positive numbers. That means I will reflect this and draw it above. Okay, that means this positive part stays and the negative become positive. And this green graph, it's a graph of my function. Okay, that means that's the way to draw an absolute value which is placed on the entire y value. Okay, and you have a nice solution. I type it for you.